In Germany, the Germans are very, very proud of their car country. Germans are very proud of their car manufacturers, be it Mercedes, BMW, or since some time now, Tesla as well. I think, or I am assuming strongly, that our next three speakers are also very proud, but not because of owning a Tesla. Actually, I think it's because of what they did to their Tesla. And they will tell us all about it. So please welcome Christian, Niklas, and Hans Niklas.
Hi, welcome to our talk, Jailbreaking an Electric Vehicle in 2023. And in this talk, the three of us will share with you how we bypassed AMD Secure Boot, how we activated some soft-locked features on a Tesla, and how we extracted hardware-bound authentication keys from Teslas. This story began around 1 year ago when Oleg approached us. Oleg owned a Tesla, actually, and was interested how its digital systems worked in detail. But ever since Tesla switched to AMD-based CPUs in their infotainment systems, he wasn't able to be the king of his car anymore. So he contacted us because we, in the past, we worked for the TU Berlin, worked a lot with AMD and especially the security of AMD processors. So why would you jailbreak a car in the first place? Like Oleg, you might just be curious how the system works. You might be interested in replacing the software entirely, or you want to change the system in a way that you, for example, activate some soft-locked features. Because the Tesla is not a mere electric vehicle anymore. They sell you stuff after you've purchased the car. For example, rear seat heaters. They are included in the car, but if you want to use them, you have to throw in another $300. So, in this talk, we will first analyze the boot and the firmware security of the infotainment system. In the second part, we will get into some electrical engineering, and Niklas is going to talk about our glitch attack on the infotainment system. And in the third part, Hans Niklas will guide you through some crypto, how we extracted car unique secrets from the car. So, if you go on eBay and have $400 spare, you can get one of these Model 3 car computers. It's normally located behind the glove box. And if you open the top cap, you will see the infotainment on connectivity ECU. To give you a more complete picture, this is the board that we will focus on. There's some cooling chassis. It's water-cooled through the main water cooling system. There's some space for GPU daughter board for the premium cars. Then there's a very interesting chip that we might want to talk about again this year. It's the autopilot that's responsible for all the driving assistant systems. And if we go back to the ICE and flip it, we will see the third important chip, and that's the gateway. The gateway is kind of the interface from the brains of the car, like the chips you see here, to the rest of the car. And it acts as a hardware firewall between the CAN bus, to the Ethernet, to the infotainment and autopilot, and so on. It's like in many other car brands as well. It's an NXP, MPC microcontroller. It's PowerPC-based, FreeRTOS-based operating system, and so on. But most importantly, it stores the car configuration. And the car configuration is the single point of truth what your car is able to do in terms of performance, in terms of battery capacity. Yes, there are Teslas which don't use their full battery capacity because you've not paid for it. And the level of autopilot, probably the most expensive feature you can unlock through Tesla's app. And one of them is also the rear seat heaters, which we were after in this research. However, there's another CPU that we feel much more competent for, and that's the infotainment APU. It runs a Zen 1 CPU, it's running a custom Linux, firmware and recovery are on the SPI flash, and the rest is on an NVMe. This one was previously based on Intel and even earlier on NVIDIA. So we're not the first ones to hack Teslas. There was a lot of work in the past, just to show you a few, and they all had in common that their threat model was that they are an outsider, and they want to have, like they are either completely remote or in physical proximity and want to either open the car, control the car, and so on. And they all found software-based vulnerabilities that were all fixed by Tesla over the air. Now our threat model is Oleg owns a car, owns a Tesla, and we have digital and physical access to the car. Whatever that means in detail, I'll show you in a bit. So we want to tweak the car beyond its normal flows to activate some features, and this also might help to lift some repair and regulation restrictions. So we're not based to software-based attacks, so let's look at hardware-based attacks in this talk. If you power the system on and hook up to the UART, you will see how the system boots and get a better picture. The x86 seemingly comes up with some core boot messages, the open source x86 firmware implementation. And you will see a few stages running, and at some point the core boot will load and verify what's called the Tesla OS loader. The Tesla OS loader itself will run, load a Linux kernel from the NVMe, and verify this kernel before it actually executes it. And in the last step, the Linux kernel will get the root file system also from the NVMe and verify it. How it does it in particular, I will show you in a bit. So we have a chain of trust during boot. Each stage checks the next one before it executes them. And if a single bit is flipped, the cryptographic signatures are invalid and the system will just not boot. So how do we get a foot in here? We want a root shell. How can you do that? Well, we could either spawn a serial shell on boot over UART, we could add an SSH key to the authorize keys file, or we add a known SSH password to an account. This all requires changes to the just mentioned root file system. So any change of that will break the last step of that chain of trust. So the Linux kernel will verify the root file system and see that there's an issue with that. How does it actually verify the root file system? Similarly to I think Android devices, it uses a device mapper target called Verity. Verity, every time a block is read into memory, it's also hashed in parallel. And then these hashes will, then alongside these hashes, you will have some intermediate hashes. So you take two hashes, hash them again, and you will form a Merkle tree. So the whole file system and its specific state up to the last bit is represented by this root hash. And this is exactly what the Tesla OS loader checks for. So we just did a very basic patch of the Linux kernel, and instead of using Verity, as you can see in the bottom left, we use the DM linear target, which doesn't do anything. And also we don't restart on corruptions, but we ignore corruptions. That was a seemingly simple patch, but okay, you've probably understood the chain of trust is now broken at a different place. The Linux kernel is now will not be verified by the Tesla OS loader anymore because the signature is broken. There's several ways to fix this. We, again, went the easiest way and looked at the Tesla OS loader in our favorite disassembler. And at some point, it will check whether the NVMe image was verified successfully or not. We'll exactly patch this conditional jump to a non-conditional jump, but then it will always verify. So you can imagine the Tesla OS loader is now the one that's not being verified anymore by the core boot. We did a very similar strategy there. Core boot uses a library called vboot that was officially introduced by Google for the Chromebooks boot security. And we patched that one. And now the system didn't boot anymore. at all. So why is that? Because of the AMD Secure Processor. You might have heard of it. It's a dedicated ARMv7 microcontroller in each AMD CPU. It actually comes up before the x86 CPU does come up, and it's highly privileged. It has a variety of responsibilities. The one that's relevant right now is it's the hardware root of trust. What is a root of trust? A thing that has to be trustworthy for anything else on your computer to be trustworthy. And it will verify core boot's integrity. So we patched that. We patched that in the off-chip bootloader of the PSP, and that didn't work because there's another bootloader inside the PSP that you can't change that will check the off-chip bootloader's integrity. So if we focus now on the AMD SP, there have been some vulnerabilities that would help us here. In 2019, there was an off-chip bootloader buffer overflow that would allow us arbitrary code execution, therefore we could skip that check. But that was fixed via firmware updates, and we didn't even find a faulty image for Tesla that would contain this one. In 2020, even juicier, there was a ROM bootloader vulnerability that, wouldn't be able to be patched by AMD without issuing new hardware. And this one was seemingly usable for us because they only fixed it from Zen 2 on, and the Tesla has a Zen 1 CPU. But apparently, Tesla gets special treatment from AMD here, and this fix was backported to the Zen 1 CPU. So if we step back and compare Tesla's security from around 10 years ago to now, they've stepped up their game a lot. Back then, they had OpenX servers. You basically were root when you plugged in Ethernet, and there was no code signing. Now they have code signing, firmware signing. They have a chain of trust during boot. Whoops. And their root of trust is in the AMD SOC. So with this situation, we had to get another weapon from our arsenal. And for that, I'm going to hand you over to Niklas.
Okay, so I'll talk about how we hotwired the infotainment system. And for this, we will first have a look at how the regular early boot verification looks like. So first, the ASP loads the AMD root key from SPI flash and computes the hash of this root key. Afterwards, it compares this hash to a hash that is stored in read-only memory. And if this is successful, the ASP loads and verifies the off-chip bootloader using this root key. What's interesting here is that Tesla has a custom root key. So as an attacker, we would now like to be able to replace this root key. And in this case, the key verification would just fail. And this also stops the boot process completely. So, but let's think about what happens if we could do something about this here. Okay, so for this, we will talk about fault injection attacks. Fault injection is a method where an attacker induces faults by altering the IC's environment. And for this, we could hit an IC with a laser or with EM radiation, for example. But we could also try to modify the clock signal or the supply voltage. In the case of voltage glitching, the supply voltage is lowered for a short amount of time, just as you can see on the picture below. So let's consider a password check where the user types in a wrong password. Normally, that check would just fail. But if we inject a fault into the processor, it may ignore the comparison. So the comparison is ignored, and the password will be just printed as correct. But in most cases, we will just introduce other errors, for example, system locks or system resets. That means that most faults are just useless for us. And that's why we have to adjust the glitch, which brings us to the three main challenges here. So first, we need to figure out when the targeted check happens to be able to precisely trigger the glitch attack. Secondly, we have to find the correct voltage drop parameters. For example, the steepness or the width of the voltage drop. And finally, it is necessary, or we need a way to identify failed attacks and retry as fast as possible. Okay, so that's from where we are coming. The ARC is replaced by our own key, but its verification is going to fail. So our plan now is to glitch the root key verification so that our custom root key is accepted. This allows us also to resign the modified off-chip bootloader, which then will get successfully verified too. And to make this happen, we first need to find out when the verification takes place during boot. Okay, so here you can see an SPI trace of the regular boot with the original root key. The only thing we can tell about this is that the root key is loaded right here, but we don't know when it gets verified. So now we flipped a bit in the root key and captured another SPI trace. You can see it here. And with this modified root key, the SPI activity stops completely after just loading the key. And that means that the root key verification must be taking place during this red dotted time window here. So afterwards, the off-chip bootloader is loaded and verified just as I explained before. Okay, so now we know when we have to trigger the glitch, but we don't know how to inject the actual voltage drop. And for this, we will have a look at how the AMD SoC is powered. So there is an external voltage regulator that is connected via its SVI2 bus to the SoC itself. And it allows the SoC to control and monitor its own voltage. There are two voltage domains, namely VSoC and vCore. VSoC is used to power the AMD Secure Processor in that case. So yeah, we would like to inject our voltage drop into the VSoC voltage domain to glitch the AMD Secure Processor. So our glitch setup looks like this. We have a TPM microcontroller that is responsible for the glitch. And this is connected to the SVI2 bus so that we are able to inject arbitrary packets into that bus. It is also connected to the ATX reset line so that we are able to reset the target. And of course, it also monitors the SPI chip select line so that the TNZ knows when it has to trigger the glitch attack. And additionally, we use an external PC to control the whole setup and to adjust the glitch parameters. Okay, so this is how our wiring looks like. We connected two wires to the SVI2 bus for data and for clock, and an additional wire to the SPI chip select line, to monitor the SPI activity. Okay, so our glitch setup looks a little more messier in reality. With all the cables and the board in the middle, it's kind of messy. So here you can see the SVI2 bus connection. Then there is the TNZ microcontroller. And we connected some more wires to the SPI bus so that we are able to debug the whole boot process and debug our glitch attack. What's interesting is that Tesla uses an HDMI connector for debugging purposes. And we were able to connect the ATX reset line, an additional SPI programmer, and the serial output just through that connector. So this additional SPI programmer is used to read and write to the flash chip directly when the board is powered off, for example. Okay, so let's go through the actual voltage glitching steps. Here you can see a logic analyzer trace of the whole glitch setup. From top to bottom, the signals are SVI2 bus clock, then there's the SVI2 data line, the target's voltage, VSoC, And there are two traces of the SPI chip select signal, one of a failed attempt and one of a successful attempt. So in the first step, the initial voltage is set. You can see the SVI2 packet, which is sent by the CPU. And this one tells the voltage regulator to rise VSOC. We use the first packet also to detect that the target begins booting, which triggers the attack logic that runs on the TPM microcontroller. After the initial voltage is reached, the voltage regulator sends telemetry packets and VSOC becomes stable. But as we would like to be able to inject SVI2 packets at any time without a packet collision, we will use the TPM-Z to disable the telemetry functionality by injecting another SVI2 command, just as you can see on this picture. And also VSOC is adjusted another time here. So in this step, the AMD Secure Processor awakens and starts loading data from the SPI flash. And that's why we see activity on the SPI chip select line here. The TPM-Z will count all the chip select edges until it is time to actually glitch the target, which is right now. So at first, the TPM-Z injects a packet to make the voltage drop, and then another packet to make the voltage rise again. And to find out if the glitch attempt was successful or not, the TPM-Z monitors the chip selector. If it becomes active again, we know that more data is loaded, which also indicates that the attempt was successful. And on a failed attempt, no more data is loaded, and the chip select line stays inactive, and the TPM-Z resets the target so that we can make another attempt. Okay, a short recap. We should now be able to circumvent this check. And we should also be able to patch all boot stages using our custom key and the glitch. And for the following demo, we have put our SSH password into the root file system, and we have connected the infotainment system to a PC via its Ethernet connection. Okay, this is our lab. As you can see, we don't have the real car, but at least we have the monitor and the infotainment board. And in this video, you can see that we haven't bought the optional rear seat heaters, of course. And yeah, so we are not allowed to activate them. Okay, this is a snippet from the car configuration. And the rear seat heaters have the ID 13. And we would now like to set this value to 1. But for this, we first need to get a root shell. In this video, we will demonstrate the glitching attack. On the right side, you can see the glitch script that runs as many glitch attempts as fast as possible. On the top left side, there is the serial console where we will see the boot log of the infotainment board. And on the bottom left side, there's an SSH console where we will log in as root. Okay, so now we'll start the glitch script, and you can see there are many attempts rushing through. This one was successful. And now we should be able to see the boot log. There it goes. And after a while, Ethernet is up and SSH is up, and we can log in. So yeah, we should now be root on that system. We will use the gateway diagnosis command to get the value of ID 13. We will set this value to 1 and see if that worked, and that worked. But yeah, let's see if we are now able to activate the rear seat heaters. So back in our lab, and after reboot, we should now be able to activate them. Let's see if that's possible now. Okay, so that worked. But yeah, let's talk about persistence. Well, the car configuration survives normal infotainment reboots, but our voltage glitching is, of course, not persistent. But also, the infotainment doesn't reboot very often, and additionally, the glitching attack could be made way more convenient using a custom mod chip or a PCB, for example. But this is more like an implementation detail, which is maybe up to someone of you. Let's see if someone will build such a device. Okay, so our demo was possible because the rear seat heaters have been an insecure configuration item that was not checked by the gateway. With infotainment version 2022.44, the item was upgraded to be a secured one, just like, for example, the full self-driving feature. Being root on the infotainment is therefore not sufficient anymore, and we would need another vulnerability in the gateway firmware to carry out the same attack again. Yeah, and such gateway vulnerabilities were presented by Zenactive at last Ponte-On, and yeah, it allowed to run unsigned firmware, which would also allow our attack again. Okay, so we got a little bit more for you. Let's see what other secrets we were able to extract. Okay.
Yeah, thank you, Niklas. So here's also Niklas, and I'm going to talk about extracting secrets from the Tesla. So we're root. We should be able to just copy off whatever we want. But what is there even? So in the first place, we have the so-called car credentials, which are just basically an asymmetric RSA key pair used to authenticate the car against Tesla servers. For example, in order to download new firmware for the car, which Tesla doesn't usually, provide to anybody. So you actually need to be a car to get it. And then furthermore, there is user data on these Teslas, a lot of, logs from your connected phones or Wi-Fi's, as well as actually, tokens for session or for accounts that you've logged into, like your Gmail, for example. And what about security? Well, it used to be that everything was basically in clear text there, which, yeah, caused some bad press. Test. There we go. So, which caused some bad press for Tesla. Here you can see that, if you buy with your 400 euros such a car computer from eBay, you can just extract data about the person whose car it was. And yeah, so that's why Tesla has changed it. And now they actually secure this using a TPM. A TPM is a trusted platform module. It's a small cryptographic module that can hold and make available cryptographic material, like, for example, the car credentials or the disk encryption key for the user data partition of the system. How is this helping? Well, the TPM will, for example, only allow you to use the car credentials if you actually it will allow you to use them if you are running on the system, but you can't copy them off of the system. So actually, whenever you want to use them, you actually need to be on the car. And for the user data partition disk encryption key, it's the same. You can't just, like previously, desolder the chip, mount it somewhere else, the NVMe chip, and access the data there. But as it turns out, Tesla uses AMD's firmware TPM implementation. And we've just actually written a paper about hacking this firmware TPM. So we should be able to still get access to this data. And previously, we were able to unseal some disk encryption keys, but actually for our Tesla work, we had to amend our previous work to actually allow unsealing arbitrary TPM objects, which I will talk about now. And so spoiler alert, we've used that to extract the car credentials from our Tesla board and also re-enabling accessing the user data off of the Tesla boards. So, in the boot process, how does this look? Well, so here's a simplified version of the boot, and you see the AMD Secure Processor boots the operating system from the NVMe, and now we have additionally this user data partition on the NVMe, which is encrypted, and we also have some more firmware running on the Secure Processor while the operating system is running, and one of the applications that's running on there is the firmware TPM application. And the operating system can now talk to this firmware TPM application, request the key for the disk encryption, and then use this key to unlock the user data partition. You see, okay, we are root, right? So we should just be able to take the key from this firmware TPM application and unlock our disk and so on, but that's actually not the case. Let's zoom in a little bit further to understand why. So first of all, this firmware TPM application has some state, right? So we have some called non-volatile data, which just is the internal state of the FTPM application, but that's really small, and TPMs don't store all of their data in there. But what they do is, for data that you might want to access, they seal it using some cryptographic, encryption seeds, and then give you the data back to store yourself. So actually, the disk encryption key, for example, is stored in the disk encryption header as a sealed TPM object. And then the operating system will load the sealed TPM object, provide it to the firmware TPM application to unseal, and which it will happily do, and give back to the operating system, and now the operating system can again unlock the disk. Okay, so let's zoom a little bit in even further. How does such a TPM object look like? It has a public part, contains a lot of metadata and so on, and it has a private part, and this private part in the disk encryption case contains the disk encryption key as well as some other data, which we'll go into a little bit later. And if you store it on your disk, then actually this private part will be encrypted and integrity protected. And yeah, for us now it's interesting how this encryption is done. And if you want to use such a TPM object with your TPM, you always have to have a parent object shown here. And this parent object is already loaded in the TPM, and it has in this private part there's also a private seed for this parent object, which is used in the key generation for the storage and integrity keys for your newly loaded object. Basically it's really easy. You take the public part, the seed value, generate some keys, and with those you can decrypt or encrypt this private part. And all of this is well specified by the TPM specification, which will be important a little bit later, because not everything is really well specified in the specification. Okay, if we think about this now, how does this look in practice if Tesla's firmware wants to use the TPM to unseal the disk encryption key? Well, we have a TPM object. In general, this is sealed by a parent object, or this could seal actually multiple objects. And in general, these objects form like a key forest, right? Multiple trees of keys. And at the top of these trees of TPM objects, we have the so-called primary objects. And the difference here is that these are not sealed against the parent object, but they're actually derived from a primary seed. Okay, and if you now wanted to access some TPM object, for example down here, right, this is your disk encryption key, then what you need to do in order to load or unseal it is you have to perform or walk down this hierarchy to get to the final object being loaded into your TPM. And so from the point of view of like the operating system, the only thing that you can actually expect the TPM to have at the start is this primary seed, which hints at the underlying storage structure, because only this primary seed is actually persistently stored in this non-volatile data of the firmware TPM application. Everything else will be derived or loaded at runtime. Okay, so talking about this non-volatile data, I've introduced a little bit. The most important thing is that it's stored on the SPI flash chip. It contains these primary seeds, which we'll need to have access to in order to unseal our disk encryption key. And of course, it's encrypted, because otherwise we could just, get the primary seeds and be done with this. So for our paper, we reverse engineered how it's actually done. You don't need to look at all of this in detail. Just at the bottom here are the keys that encrypt our non-volatile data. And actually in the middle here, you see that there's some data mixed into this key derivation, which is actually, turns out, is the AMD root key. And now the issue is, right, in order to get root, we actually replace this AMD root key to sign our own payload, which then would boot the next step that we've modified, and so on and so on. And the problem is that with this modified AMD root key, we now get different keys, and the firmware TPM will not be able to load the data, the non-volatile data, and so we can't use it to unseal any of the TPM objects that we want to get access to. Okay, okay, that's why we're even here. So let's continue. How can we circumvent this? Well, we just have to leak the values before it. At the very beginning of this key derivation, there's a random, I think 32-byte value that is used to actually generate a different key for every processor. Right? You can't have the same keys for every processor, otherwise you could just take this non-volatile data, put it in some other AMD processor and unlock it there. And we want to get access to that. We can't do this actually. We have to go one more step down in this derivation process and leak a later part of this key derivation. Here we go. So how is this key derivation performed over the boot? Well, basically, you just have this decrypted non-volatile data, and you have the seed, this intermediate value that's passed on all the way from the AMD ROM bootloader to the FTPM application. And with our glitch attack, right, we are able to replace the off-chip bootloader with our own payload and execute whatever we want there. And so what we did is we just executed a small payload that takes the seed and leaks it over the SPI bus to the outside. Okay, so let's take a view at this hierarchy again, right? Remember, we want to unseal this object, we want to perform this hierarchy walk, and first of all, what do we need to do all of this? We have access to this TPM object because it's just stored in our disk header. Any intermediate objects we assume to have also access to, and also the sealing step is actually well specified, so we know how to do it. But how do we get to this primary object? Well, in our paper, we're actually done here because they used some it was difficult to compute, so they just cached this object in the non-volatile data, which we just showed you how we can unseal it, and we were done. But for Tesla's case, actually this primary object is derived every time from the primary seed, which we do have access to, but we still need to do this derivation step. And the problem here is that this derivation step is not really well specified, so we had to reverse engineer it, which actually took us a lot of time and was kind of under pressure because we had already announced that we were going to do a talk about this. So I'm going to skip this, how we actually reverse engineered it. We reverse engineered it, it was great. Now we're at this step here. We did the reverse engineering. We do have access to this non-volatile data because it's just on the SPI flash chip. We have leaked the seed value, which we can use to decrypt the non-volatile data, and we can just extract this primary seed from here. Okay. If you've fallen asleep during all of that, now comes the practical part where I show you how this looks in practice. And this is my terminal window, and you can see that we've extracted some PEM-encoded data from the Tesla's file system. This PEM-encoded data can actually only be used if you have access to the correct TPM module, because it needs to be used with a TPM because it is a TPM object. And I don't have access to the correct firmware TPM right now, but I'm on my home machine, and I've written a Python script here. You can see this Python script takes as inputs actually the the flash chip data that we extracted from the Tesla. It takes the seed that we extracted from the Tesla, and it takes this TPM object and gives us a clear text version of this RSA key, which we can now hopefully use without any problems. The next thing that we needed to do, we extracted these car credentials, is actually just perform a GET request, authenticated with OpenSSL to Tesla's production servers. We have here some certificate for our car credentials, as well as the just unsealed car credential plain text file, clear text file. And this request successfully gave us back a lot of metadata, that was our proof that we had actually gotten access to the correct car credentials in clear text. The next thing here, you can see it's a looks header for the user data partition. At the bottom, there's again a TPM object, which we can unseal with a similar Python script. And finally, we can mount this encrypted user data partition, which contains a lot of user data. Here I've just mostly blurred everything, but you can still see that this person had some contact named Alice in their data. All right, so that concludes this last part of the presentation, and we'll summarize. We've reverse engineered all of the boot security of Tesla. We found it to be rather good, to be honest, but still were able to exploit it because, the CPU they used wasn't hardened against voltage fault injection attacks. And we used that to show you how to unlock some soft lock features. And of important note here is actually you can't patch this by software because you would need to patch the hardware because we attacked the ROM bootloader. You can't patch that by software. And lastly, we are able to use this attack to also leak some secrets that Tesla would rather not have us leak. The key takeaways here should be that if your threat model includes the owner of the system, of course, being locked out from some features, then you do need to have hardware attacks in mind. And actually, also a positive takeaway might be that using this well-hardened open source software like Coreboot or Linux seems to actually work pretty well, because up until this point, it seems like the car hacking community didn't have any way to get root on the AMD-based Tesla boards. All of this was, of course, responsibly disclosed and so on, and Tesla informed us about the car configuration not being insecure anymore, so you can't actually do the rear seat heater unlocking anymore. You would need a different or a further attack. And with that, I want to thank Christian and Niklas and Oleg for their work. And if you want our code, it's available on GitHub. And I hope we have some time for questions.
Thank you. Thank you so much to the three of you. You can come to us. Yes, please. And we do have time for questions. So, I already see a hand. Sorry.
Thank you for the talk. I really enjoyed it. As I have experienced how these seat heatings work, they are connected via LIN or CAN. So wouldn't it be much easier to just have a little bit filter device, something that just via CAN or LIN activates the seat heating without needing to hacking the CPU and stuff?
Yes, would be easier. You could actually hotwire it, right? I mean, but that would be too easy.
Okay.
No, you're right. It's not the easiest way to go.
Little fun fact, because you showed the back-end API of Tesla, that is called Mothership, and like 5-6 years ago, it was still possible to access that via the VPN, but without any SSL client key. And with just giving the VIN, you could get the root password for each Tesla car.
Nice.
Very cool. More questions?
So I was wondering, how do you know which contact to hotwire? Is it documented, or is it just try and error?
Sorry, I didn't understand the question.
On the main board, the contacts.
Yeah.
How do you know which one to hotwire and which not?
So that's actually a good question. So these voltage regulators, we've done this attack a lot on AMD processors, and these voltage regulators can be easily identified because they have a lot of big capacitors and big spools. What are they again? Yeah, big inductors next to them. And you can usually then just have a guess. This is my chip. Google it and hopefully find the correct thing. And if not, then you can also just connect the logic analyzer, look at the signals, and actually these SVI2 packets look a certain way. We are now pretty good at identifying them.
Yeah.
Thank you for a great research and presentation. I'm just out of curiosity, how long does it take, like the whole research? Like it was a year, a week, 2 days?
So, I mean, we did the most relevant previous research on like glitching an AMD CPU before we looked at Tesla even. So that was an important kickstart in the whole project. We didn't work full time on it, but we started, I think, in fall last year. We got the first board, yeah. And then, tried. And sometimes when you do, for example, the parameter search for the glitch, it also takes maybe 5 days or a week until you find the correct delay and duration and so on. So sometimes you can't really accelerate the process and just have to wait. But yeah.
Sure, thank you.
First question is, how big is the glitching window for the verification?
I think it's like 50 microseconds, 50, 60 microseconds.
And the second question is, you said you're doing a lot of glitching research on AMD CPUs. Since when are you doing this? And because it's like a big window and it's pretty easy glitch, and I'm a little bit surprised that it's working on the platform security processor.
Yeah, we too were surprised. So actually this was my so building this glitch setup was my master thesis, and I think maybe 2 years ago, probably 3 years ago, and since then we've just it continues to work, and we continue to think of new paper ideas for our PhDs. So. But yeah, I mean, maybe a little bit. It was my first ever glitching attack actually to do, and it's a pretty inefficient setup because you saw the voltage go down really slow and go up really slow, and you can in theory it could be much improved a lot, but it's just an easy thing to not worry about capacitors, not worry about anything, just connect your digital pins and inject 2 packets. And the pretty big windows, so usually we have like 1 day of just, going through all of the parameters, and then we find one that fits, and then we just spend a few more hours optimizing them. Actually, in the Tesla, we had some false positives, which were really annoying. So glitches that seemed to work, but did not work for real. I don't know. Okay.
Would be time for one last question.
Yeah, thank you for the great talk. What I'm personally most honor is your way of problem solving. So to my mind, it wouldn't be logical to start at the end and solve each. I simply can't just call it a step, but a stair you solved in that way. Is it your default way of solving problems to start at the end, at the goal?
No, I think it's not our default way. But you referring to the boot security patches and so on. Yeah, we had to start somewhere, and then I guess that's maybe the software engineering way of, like, you try it and then it doesn't work and you fix the next problem until you don't have any problems anymore. Maybe that was the philosophy. There was no philosophy. We just, I don't know. That's how we did it.
It may be also, so we didn't start exactly in the order that we presented it. We had like code execution on the AMD Secure Processor as a first thing, and then made the attack work from there on.
All right. Thank you so much for the talk. Thanks. Already set up your laptop. Wonderful. Our next speaker brought some more extensive demonstrations, so I hope it will work.